Hello, my name is Christopher Roy. I'm an orator and technician at our CSN Planetarium here in Las Vegas, Nevada, where you too can experience our desert skies. Come with me and we will explore the latest in astronomy and astrobiology. For centuries, humankind has been contemplating the existence of extraterrestrial life. Since the first confirmation of planets outside of our solar system in 1995, and the discovery of thousands more of these exoplanets to this day, we have opened a kind of Pandora's box in our quest to survey the sky. We have answered the question of whether our system of planets is alone in the cosmos, and we are delighted to find that planets are seemingly everywhere. The caveat, however, is that these exoplanets are in star systems that are light years away. It would take our current spacefaring technologies hundreds or even thousands of years to physically visit and sample these worlds. For now, our only resource of information about these distant worlds and any life that they may host is from the light that we receive through our most sophisticated telescopes, combined with a little creative techniques. While we discovered over 3,000 exoplanets, we cannot see any of them clearly enough to simply look upon their surface and see if there's anything crawling around. They're simply too far away. Even from a few hundred miles above our own planet Earth, it's difficult to see evidence of life without serious scrutiny. Luckily, we have tools and techniques which allow us to see these planets in other ways. But wait, if we struggle to see most buildings here on Earth from directly overhead, how can we possibly know about these worlds that are light years away? Enter the refined science of spectroscopy. What is spectroscopy, you might ask? Well, let's start from the beginning. In the 17th century, Sir Isaac Newton used prisms of glass to take in white light from the sun, disassemble the rays, and display the light as an ordered array of colors. Following Newton's experiment with colored light, another scientist named William Herschel performed his own experiment seeking to measure the temperature of each color of light. Herschel understood that a proper scientific experiment needs a control instrument, apart from those being tested, with which to compare measurements. So, after Herschel placed a thermometer in each color of light, he placed one more just outside of the red end of his spectrum where he saw no light at all. Herschel expected that this control thermometer would simply read the ambient temperature of the room, but to his astonishment, the temperature reading skyrocketed higher than all of the others. Herschel had discovered less than red or infrared light. Soon after Herschel, another physicist named Johann Ritter knew that silver chloride decomposes in the presence of light, but he found that this process was most efficient in the presence of what he called invisible radiation beyond the violet end of the light spectrum. This radiation became known as ultraviolet radiation. The combination of all these types of light, visible and otherwise, we now refer to as the electromagnetic spectrum. There's one more gentleman who took the study of the electromagnetic spectrum that one step further. A Bavarian optical lens manufacturer by the name of Joseph von Fraunhofer. Joseph von Fraunhofer. Fraunhofer noticed that light passing through a chemical before being refracted by a prism would ultimately produce a light spectrum with dark lines, as if certain wavelengths of light were missing. Furthermore, the location of these dark lines varied depending on the chemical that the light had passed through. The chemical seemed to be filtering the white light by absorbing specific wavelengths of energy and allowing the rest to pass through. Fraunhofer had developed the first spectroscope. Today, we use Fraunhofer's technique to observe the spectra of light from distant stars and planets, and to discern what elements and molecules they are made of. This practice is known as spectroscopy. Astronomers then go on to share and compare light data with people of other scientific disciplines such as chemists, geologists, and biologists, and by pooling their expertise in these various fields, scientists can begin to draw reasonable conclusions regarding the size, composition, and environments of these distant worlds. In the search for extraterrestrial life, we have conversations about what types of chemical features may hint toward life as we know it on other planets. Or perhaps there are entirely different forms of life, unlike anything we've ever imagined. But here on Earth, we know of several chemical biomarkers that we are intimately familiar with. Water, for example, is critical for biology on our planet, and may be a great place to start when looking for life elsewhere. On the other hand, water does not need life to exist on its own. Water may be great at supporting life, and it is found on most other bodies in our solar system in some quantities, such as Europa and Enceladus, and even small traces on our own moon. But water alone won't let us know that life is in fact present. Perhaps there are better biomarkers than water, chemicals that break down easily over time, and so do not easily exist without being continuously replenished in the environment. Oxygen is the third most abundant element in the universe, but it's incredibly reactive and easily bonds into other chemicals and complex molecules. Rarely do we find molecular oxygen, just the O2 by itself, in nature, except for here on Earth, where it is processed out of carbon dioxide and water molecules by the photosynthesis of plants. Some other examples of byproducts of life include carbon dioxide, ozone, methane, and phosphine. Now, some of you may be thinking that last example, phosphine, sounds familiar, and it should. One of the latest scientific developments reported in the media comes from an announcement that a team of scientists using spectroscopy have found spectral signatures of phosphine in large quantities on our nearest celestial neighbor of all things, Venus. Oh. Why is this such big news? Phosphine is significant because it is unstable and will quickly break down when exposed to other chemicals or light. Furthermore, as far as we know, phosphine isn't easily produced on small rocky worlds. We've detected it in large quantities on Jupiter, but gas giants are entirely different chemical engines than our smaller rocky worlds of our inner solar system. To better illustrate the significance of this recent find, let's take a look at our nearest neighbor, Venus. Venus is a rocky inner world in our solar system. It has an atmosphere. It is roughly the same size of Earth, about 90% of Earth's volume, and the similarities pretty much stop there. Venus rotates extremely slowly on its axis, and in the opposite direction of all the other planets, except for Uranus, which rotates on its side, which is just plain weird. But comparing with Earth once again, one day on Venus is equal to 243 Earth days. That's a lot of sun every day. Furthermore, while 1 year on Venus is only 225 days on Earth. Now, looking at these numbers, there's something a little funny. One Venus day is 243 days, but one Venus year is only 225 Earth days. This means that one day on Venus is longer than its year. Furthermore, all of our past probes have shown that the Venusian environment is extremely hostile to life as we know it, both biological and mechanical. At the surface, temperatures exceed 900 degrees Fahrenheit and it can melt lead, which is why the longest a lander probe has ever survived on Venus is a remarkable 127 minutes. The atmospheric pressure at the surface is more than 90 times that of Earth at sea level, and comparable to diving half a mile underwater. On Earth, we are aware of our carbon and water cycles in our atmosphere. On Venus, this is replaced with a sulfur cycle, which involves the possibly geologically active surface and the vast, chokingly toxic clouds that rain sulfuric acid from the sky. This highly acidic environment would be detrimental to most life here on Earth. In short, if you were to visit Venus's surface, the planet would crush you, dissolve you, and then burn your remains. So why would anyone think that life has any chance on Venus? Well, while the surface is most uncomfortable, the upper atmosphere is a different story. About 35 miles up into the clouds, it is still rather acidic, but the atmospheric pressure and temperature is similar to what we might expect to experience here on Earth, and we are certainly aware of rugged extremophile microbes that are rather comfortable in acid environments, such as the acid pools in Yellowstone National Park. It may be the case that similar microbes are thriving in the balmy clouds above Venus and are responsible for the phosphine gas as a byproduct of their metabolism. So, time to take a step back and think objectively. There are three possibilities surrounding the phosphine gas phenomenon. First, there is indeed microbial life thriving in the Venusian atmosphere and producing this chemical biomarker. Second, the presence of phosphine around Venus could turn out to be due to abiological or inorganic processes, such as geochemical processes with rocks and volcanoes, or photochemical reactions with sunlight radiation. Thirdly, the last possibility is that the data collected that is suggesting this gas may simply be in error. We will have to wait for these findings to be verified by independent teams of researchers before concluding that phosphine even exists on Venus in the first place. If phosphine gas is indeed present on Venus, then this is a legitimate mystery with a valid logical path to infer the possible presence of life. With that said, it is important to remain cautiously optimistic until much more data is available to us. Dr. Carl Sagan was an enthusiastic astronomer, planetary scientist, astrophysicist, and science communicator who made great strides in educating the public about what it means to be scientifically literate. He famously stated that extraordinary claims require extraordinary evidence. And these words couldn't be more fitting in this evolving story surrounding these claims. When we have results that are interesting and unexpected, they naturally attract more scientific scrutiny to see if they are correct. This is a natural urge that a scientifically literate mind must have. I, for one, will be thrilled if we find extraterrestrial life right here in our cosmic backyard. This could mean that if life has spawned twice in the same solar system, on vastly different worlds, life could be everywhere in the cosmos. It is quite likely, though, that this discovery turns out to be something else. That would be fantastic as well, because that means we have learned something. This is the greatest thing about science. Even if you're wrong about your initial hypothesis, it's okay because you still win a trophy of knowledge just for trying. My name is Christopher Roy. I hope to see you soon at our CSM Planetarium, and keep your eyes on the skies. Thank you.